Hello everyone. In this recording, we are going to solve exercise 2, uh, which is the delivery schedule. So it says that we have a delivery company operates in three regions, A, B, C. Each delivery requires fuel and generates a certain profit. The company must schedule deliveries so that the total profit is at least a given guaranteed amount, which is the capital P, and the goal is to select deliveries that minimize the total fuel consumption. So we have feasibility rules. The first one is that the total profit should be greater than or equal to P, and we have to have at least one delivery from each region. Then the objective is, as it says, minimizing the total fuel consumption. And we have these four instances: toy, small, medium, and large. And here are the tasks. So we need to perform task 1 to 5 as described in general instructions. When running your algorithm on a small, medium, and large instances, report should be the output, and the report should include deliveries, total fuel consumption, total profit, and feasibility confirmation. And you need to also provide your answer using the answer template file. Okay, so we go back to task 1 to 5. Here we are. Okay, so first one is to the pseudocode adaptation. So write a pseudocode of a random search algorithm for the exercise by adapting the generic version provided in figure 1. Specify how to random solution X is generated, how a random solution X is generated, how you check the feasibility, and how you evaluate or compute the objective function. So this is the first one. So we need to adapt the pseudocode in figure 1, which is a general random search algorithm, this one. To do that, we can simply copy paste this one to Word document and try to modify that based on our problem. So here we have that pseudocode, general random search algorithm pseudocode, and here are the lines. So the first two are the same for all the problems that you have. So the first line is about the input of your pseudocode and eventually your code, which is the problem data, and of course the maximum number of trials, and the output is the best solution that is found. So we can make it a little bit specific, so we can say the best solution and also the best value. And for each problem you are looking for the best solution and also its value. So the third line is that the best solution is, which is a variable here, is null, so we don't know it, the best solution yet. And we have also the best value, which is a very bad value in our case, because in the problem we are minimizing the fuel consumption, so we can choose a very large number in this case. So if we go back to our pseudocode, we can have, let's say we can have infinity here. So I'm going to insert this one, so we can set the best value to be infinity, which is a very large number, but you can make, if you don't want to use this one and you want to set it to an actual number, the only thing that you need to do is to go back to your, for example, we are working on, let's say, the toys instance here, and here are the fuel consumptions. So if you choose a number that is greater than or equal to the summation of these numbers, so that number is enough for your pseudocode or for your code eventually to start from. So let's go back to this one. So we have the best value, which is a very large, a worst number. In our case, is a very large positive number. And then we have our for loop. So it said for trial 1 to max trial, which is the maximum trials that we wanted to do, is do these lines of code eventually. So it's the first one is generate a random candidate solution S. So to make it specify, we know that we wanted to select deliveries from different regions, so we can make it more specific and generate a random binary vector or list, and we can call it S, or we can call it X as it says in the description. So let me change this one to this. Okay, so we have a random binary list, or we can call it X, or we can call it solution, whatever you prefer. Let's say binary solution, binary vector X. And then number 7 says if S is feasible, then do something. So for checking the feasibility, if we go back to our problem description, we need to check these two rules. The first one is we have to make sure that the total profit is greater than or equal to the capital P. Going back, so first we need to calculate the total profit. So if you go back to our code here, before checking the feasibility, we need to calculate the total profit. So we can say calculate variable total, we can call it total profit. And how we are going to calculate this one, so the total profit is going to be we can continue this one. So this is going to be the summation over all of the elements that we have as a solution, and we multiplied the corresponding values in the solution by the values that we have in the profit parameter, so which is a list actually in our problem. So each of those here we have, so eventually we will have an X, and then we need to multiply those X to their corresponding values in the profit vector or profit list or whatever you call it. So we need to do that, and we need to add them together to have the total profit of that solution. So what we are going to have here is that we have a summation over I, which is the index of each delivery in our X. And how we are going to do that, we are going to multiply X I, which is index I of the solution. We multiply this one by its corresponding value in the matrix of the profit. So I'm just simply, sorry, the vector of the profit I. Okay, so this is what we have. So we sum over I, which is all of the deliveries, xi multiplied by its corresponding in the list or the vector of the profit, which is one of the inputs of the pseudocode. So with this one, we can have the total profit, and later what we need to do is to check this one in the feasibility if this total profit is greater than or equal to the capital P. But before that, we have other rules. So going back, we also need to check that we have at least one delivery from each region. So one thing that we can do is to make it use a mathematical terms here, but we also can just simply say that check if we have at least one delivery from each region. Okay, so this is the second thing that we need to do that. And for this one, we can define some variables here in the pseudocode, but yeah, let me do this. So one thing that we can do is, let's see what we can have here is, can define some variables. Yeah, we can define some variables here. I'm going to call them simply has A, has B, and has C. Make it this one has A, has B, and has C. Check if those are true, or we can say are, yeah, I can, nice, are true. So we need to define some variables. So in our case, we define these bool variables, has A, has B, has C. And we wanted to make sure that if they are true, which means if they are true means that we have at least one delivery from region A, one delivery from region B, and one delivery from region C. Okay, so we also need to check this one. This one is actually, we can also have this one equivalent to, you don't need it to have it in your pseudocode, but I'm just telling, say, writing it for you. So it's equal to that we have at least one delivery from each region. Okay, so this is equivalent to this. So if they are true, check if this, or I can make it more specific, and in and true, all of them are true, then it means that we have at least one delivery from each region. Okay, so this is what we can have here, and I'm going to get rid of this one. Okay, so these are the two rules that we need to check. So if both of them are satisfied, then we can say that the X is feasible. So for checking that one, we can say if X is feasible, or we can say if the total profit is is greater than or equal to the capital P, and this one, this is the second condition, the second rule, and we have this one, and has A, has B, and has C are true, which means all of them are true, then we can compute the f of s, which is the objective function of that solution. How we are going to do that? First of all, we need to define another value. So we are going to call it the total fuel, and this one is going to be the same. The calculation is the same as the total profit, but this time we replace the profit vector or the profit list with the fuel list. So we can paste it here, and therefore xi multiplied, instead of profit we have fuel of I. So this is how we are going to calculate the total fuel. So let me just check one thing here, if it is, yes, it is greater. Okay, so we have those rules, we check them, we calculate the total profit, and we also check that if these are true, and then we put all of them together. We had in total 4 rules or 4 conditions to check, and if all of them are true, we have and between them, then it means that the solution X is a feasible solution. Then we check the total fuel, which is the objective function of that solution. And now we need to see if this solution is better than what we had so far or not. And so instead of f of s, we can have if the total fuel is better than the best value that we have. In this case, is better than means is sorry, less than or equal to the best value, then the best solution is going to be x, and the best value is going to be the total fuel. One thing that I can do to make it a little bit easier for you, we can call it the total profit of x, for example, to make sure that this belongs to the x. And also I can do the total fuel for total profit of x is greater than or equal to b, which, make that a little bit maybe easier to understand that we are actually doing this for the x, and this is going to be the total value, total fuel of x. So, and then this is the end. So we end this if, and this is the end of that if that we are checking the feasibility, and this is the end of the pseudocode, which is the end of the for. So we do this for the maximum trials that we wanted to do. So again, we started from having the input or the parameters of the problem, the maximum trial, the problem data, and what we are looking for is the best solution and the best value. So at the beginning we set the best solution to null and the best value to a worst possible solution, a possible value, which in our case, because we are minimizing, so we set it to be to set it to be infinity. You can have let's say in this case 1000 or even 100 are good to start for this specific problem. And then we have the body of the pseudocode. This is the outer loop. We're checking for the number of trials that we want, so we generate a binary vector because this is a selection problem, and then we calculate the total profit, and also checking that if we have at least one delivery from each region. Then we check the feasibility of that randomly generated solution. If it was feasible, we check that if this is a better solution than what we had so far or not. And if it was, then we replace this solution, this randomly generated solution, with what we had so far. Okay, so this is how we generate this. We adapt actually or modify this pseudocode based on our problem. So going back to the tasks. So the second one is to manually run the trace table using the toy instance. For doing this, we have this. I have all the parameters and the values of the toy instance here. So we have 6 deliveries, and these are the regions. The first 2 belongs to region A, the next 2 belongs to region B, and the last 2 belongs to region C. This is the fuel vector, this is the profit vector or the profit list, and this is the minimum profit that we are looking for. So we need to randomly generate some solutions. So I'm going to start with the simple one. So all of them, I said all of them equal to 0. And we have 6. So we have 6 zeros. So we go back to our pseudocode and try to see what is happening. One thing that I can do is just copy paste the pseudocode to this file and see it works. Okay, so first thing, we should set the best solution. In our case is the x best to null. So at the beginning this is null, and so let's say it's null, so we have this null, and the best value is infinity. So this is the first trial. So we generated a random binary vector which all of them are 0, and then we need to calculate the total profit, which is multiplication of each item by its corresponding value in the profit vector or list, and then summation over all of them. Since all of them are 0, so the profit is going to be 0. And then we should check if we have delivery from A, B, and C. In this case, we don't have anything, so I'm going to just simply have 0, 0, and 0. We don't have any from any of those regions. And so we check, then we go to the next line, so we check the feasibility. Is it feasible? Of course, it is not feasible because 0 is not greater than or equal to 10, and also we don't have any delivery from any of the regions. And so next one, since this is not feasible, so we don't need to calculate the total fuel, and we go back to the next iteration. So in the next iteration, so the best value so far is infinity, and the best solution is also null. So if we go to the next iteration, I'm going to change two of them, this one and also this one, to 1. So we need to calculate the profit. So what is the profit this time? This is going to be 24. So we have these two selected. So this is going to be 24. And now we are checking the region. So we have 1 from region A, we have nothing from region B, and we have 1 from region C. So this is our checking the second rule. And now we need to check the feasibility. So the profit 24 is greater than or equal to 10. So this is true. We have 1 from region A, so this is also true. Has B is also false here because we have nothing from region A, and this one is true because we have 1 from region C. But since we have 1 false among those 4 conditions, so the value of this expression is going to be false, and therefore the solution is not feasible. And since this is not feasible, we are going to skip that block of code or those lines, and we go to the next iteration. So therefore the best value is still infinity, and the best solution is also null. Then we go to the next one, and we are going to have this one here. So I'm going to change one of these zeros to 1, and now we need to again calculate the profit. So profit in this time is going to be 34. And what about the regions? This time we have 1 from each region, so we have all of them are equal to 1. And now that we want to check the feasibility, yes, 34 is greater than or equal to 10, and we have at least 1 from each region, so this is a feasible solution. Since this is a feasible solution, we need to go and now calculate the total fuel. So we are going to go here and see what is the total fuel. The first one 8, the first one 7, 15, 15 plus 8, 23, so the total fuel is 23. Now we are going to see if this solution is better than what we had so far or not. So the total fuel 23 is definitely less than or equal to infinity, so this is a better one. So now here we can update the best solution and the best value. So the best value here is going to be 23, and the x best is going to be this solution that we had so far. It's not going to be null anymore. And here we go. Let me, if I can make it a little bit, yeah, I can make it. So I'm going to make it this one, this one. So we can have all of them as a row. Okay, so here what we have. So for the next iteration, Control C, and we're going to have Control V. So I'm going to make another 0 equal to 1, this one. Now we are going to check the profit. So checking the profit, we have, so previously we had 34. I make this one equal to 1, which is 15, so it's going to be 49. And again, we have at least one from each region, so it's still the same. We can make this one equal to 2, but 0 here means that we don't have anything from that one, and 1 means we have at least one. Since we have 2, it is still going to be 1, so you don't need to. Or if it is more reasonable for you to change it to 2, it's okay, you can also do that. So here we are checking the feasibility. 49 is greater than 10, and we at least have one. So this is going to be another feasible solution. So again, we pass this line, and so we are going to calculate the total fuel. So what is the total fuel? In this case, it's 8 plus 10, 18 plus, so it was 23. I add this 10, so it's going to be 33. So now we are going to see if this is a better solution or not. So the total fuel 33 is not less than or equal to 23, which means this is not a better solution than what we had so far. So we are not going to update it. So again, after this iteration, the best value is still 23, and the best solution is what we had so far. We don't need to update this one to anything else. Control V. And finally, for the last iterations, what I'm going to do is to change this one to here. I'm going to change this one to 0, and also going to change this one to 1, and this time make this one to 0. Okay, so now let's calculate the profit for this one. Based on what we have, it's 9 plus 15, which is 24, plus 12, it's going to be 36. And we have one from A, one from B, one from C, so this is also satisfying this one, so it's all of them are going to be 1. And since we have at least from one region, and 36 is greater than 10, so this is another feasible solution. So now we need to calculate the fuel. So here we have 6 plus 10, 16, plus 8, 24. So we have this 24, and again, when we are comparing to 23, this is close, but this is not better. So we are not going to replace even this feasible solution with the previous one, because what we had previously is better than what we found in this feasible solution. So after 5 iterations, this is the best value that we find, and this is actually the best solution that we had. So now we are done with the second part, which is manually running the pseudocode and completing the trace table. Now in the next step, we need to convert that pseudocode to a Python code and check the correctness of the Python code, and finally running it for larger instances. So I'm going to conclude this recording here, and I'll see you in the next recording.